Second talk this morning is by Antoine Mellet from Ireland.
Thank you. Right, so thank you very much. So thank you, of course, to the organizer for this invitation. And so I will be talking here about some recent work that were done in collaboration with Henri Berestiki and Gabi Steinbach. So well, Henri is a mathematician, but Gabi is a biologist in the biology department at the University of Maryland. And I'll be showing a few videos that she shared with us of her experiments. And the first one I wanted to show is this one. So this is the first video that she showed us and motivated this work. I mean, got Henri and I interested. And so what this shows is some video is showing some bacteria that are proliferating on some media, and the whole colony is growing and in size. And what we thought was interesting here is, of course, Henri comes from the world of reaction diffusion equation and spreading of invasion and all of those things. And what was noticeable in this case was how different this is from the usual mechanism that we think of when we think of ecological invasion, for example, in that the cells don't move. Those are immotile cells. There's no movement really of the cell. But of course, when they experience mitosis, they double in size. And in that process, they are pushing the other cells, the nearby cells. And this leads to this expansion in space of the colony. Despite, again, the lack of movement of individual bacteria. So the idea here is that the proliferation of the spatial expansion occurs because this mitosis, and together with this overcrowding, there's a notion of saturation here. Of course, without saturation, growth would happen only locally, but this with saturation creates some pushing, some mechanical pushing that leads to the expansion in space. And we wanted to find a good model to capture this. So I'll first review some of the classical PDE model for range expansion, and mostly reaction diffusion equation and some of the extensions, and then present the model we came up with, and I'll discuss a bit the mathematical properties and some numerical simulation. Right, so when we think of range expansion like this, we often think, as a mathematician, we like to think of reaction diffusion equation, and mostly the famous Fisher-KPP equation, which is really a cornerstone in ecology, especially when they want to model the invasion of some species, some pests or anything. And in this equation, there are two phenomena really that are taken into account. One is the linear diffusion that models some kind of random motion of individuals, and the growth term, the reaction term on the right-hand side, which is a logistic term. And because it takes into account the idea that at low density, yeah, you may have exponential growth, it's u equal u, but there is a carrying capacity fixed here to be 1. So there is a competition for resources, right, that limits growth. Okay, and so together, those two mechanisms, diffusion and logistic growth, leads to this expansion in space, right? The spreading of the population, and usually described by traveling wave solutions. So traveling wave solutions are very particular solution of this form, right? They have a certain direction E of propagation and a speed C. And the typical result for this KPP equation is that there are traveling waves that describes the invasion of the stationary state 0 by the stationary state 1, right? And such traveling wave exists for every C bigger than some C star, so the minimal speed. And we know that this minimal speed, this C star, is the speed that describes the expansion of initially compactly supported solution, right? But the key feature here really for this equation is something that takes into account individual movement, this random motion, and competition for resources, right? So none of those really apply to our setup, where our bacteria are immotile, and there is no issue with resources. The experiment I showed you, there's plenty of nutrients available to those bacteria. Now, if you move away from ecology, and especially in the context of tumor growth, there's been a lot of work done on some variation of this KPP equation when you put nonlinear diffusion instead of the simple linear diffusion, right? So the equation looks a bit like KPP, but now there's this pressure, this P, right? The pressure typically taken to be u to the power gamma. You can take something else, but this is a simple case. So here are some classical references in the context of tumor growth. The idea here is now that instead of the linear diffusion, you have this nonlinear diffusion that really is meant to describe the fact that cells move away, are being pushed away from crowded regions. This is more in line with what we observe in our experiments also. And so there's some kind of Darcy's law at play here. And then the growth terms, the reaction terms, the U, instead of U1 minus U, we put U1 minus P. And the idea is that, again, what limits the growth eventually is not the fight for resources. I mean, it could also be, you could add some things, of course, in here for resources. But here we want to take into account the competition for space instead. So it's P is often called the homeostatic, I mean, 1 in this case, sorry. 1 would be the homeostatic pressure. So when P is 1, right, there's too much pressure, the cells are bunched up on top of each other, and they can't grow and duplicate. There's no more mitosis. Right, so here you need really high density to spread, right? There's this accumulation of density that pushes the cell out at the level of math. We say that the traveling waves for this solution are what we call pushed front, instead of the so-called pulled front of KPP. But the result is similar. They are traveling wave for this type of equation for all speed bigger than some C star. One interesting difference in this case is that this traveling wave with the minimal speed, the traveling wave with speed C star, is compactly, I mean, semi-compactly supported, right? In the sense that it's compacted on the half line from minus infinity to, let's say, 0, right? So, and that's because we know that the degenerate diffusion, right, preserves this compact support property. So again, this minimal speed traveling wave is the one that will describe, right, the propagation, the spreading of solution that was initially compactly supported. Okay. So now it's a bit different from KPPs. This range expansion, right, is due to growth and competition for space, really, right? It's this competition for space that pushes the cells to move out. And this is a little bit more explicit if we take these interesting limits. So formally, this would be obtained by taking the limit gamma goes to infinity, right? I said earlier here in the model, I would typically take P to be U to the power gamma. When gamma goes to infinity, what happens is, well, U is less than 1, so it goes to 0, and when U is bigger than 1, it goes to infinity. And so now we're in a situation where we're saying that until I reach U equal 1, so as long as there is room around, the pressure can be 0, and there is only local growth, right? Because when UP is 0, the equation reduces to dTU equal U. Right? But once P equal 1, the pressure kicks in and starts spreading things. And so what you get is the equation looks exactly the same, of course, as before, but now P is given by this P infinity of rho, of U, sorry. And this is often called the Illy-Shaw graph condition. You can rewrite it in this form in some ways, right? This condition enforces that U less than 1 because the pressure that I want to be infinity, pressure is now negative. And this one says either U is less than 1, or if U is less than 1, either U is less than 1 or P is 0, right? So if U is less than 1, P has to be 0. And this is called the Illy-Shaw graph condition because then this equation reduces to this free boundary problem that I write here, which is the Illy-Shaw free boundary problem, right? You can see, so when U is 1, dtu is 0, and U is 1, so you end up with Laplace minus Laplace U equal 1 minus P. So that's the equation for the pressure in the set where U is 1. When U is less than 1, the pressure is 0. So as I said, you just have exponential growth. And then there is a condition on the jump of U at the free boundary, which tells you that the speed at which the saturated region is growing, right, is proportional to the gradient of the pressure. Okay. And right, and you can make this a bit cleaner by showing that if U is a characteristic function, often we talk about patch solutions, a solution where U is either 0 or 1. So if U was either 0 or 1 initially, then it remains the case for all time, and then you really have a clean Illy-Shaw type free boundary problem. And so the mathematical study of this limit gamma goes to infinity goes back to this work of Pertam, Quiros, and Vasquez back in 2014. And there's been a lot of work on this and variants of this model since. Okay. Let me mention some other generalization of KPP, in particular ones that involve non-local term, because this will be important later. So another classical generalization of KPP equation is to replace the Laplacian by a non-local jump type operator that I wrote here. So now it means that things can jump from one position to another with some probabilities that's represented by this kernel J. And another very classical generalization is a KPP equation with a non-local competition for resources. So instead of the usual u1 minus u, we put u1 minus some convolution of u with a kernel. And the idea here is that because your individuals can move around a little bit, they will proliferate if there are resources nearby, not just where they are, because they are able to go around and look for resources around. Right? Now, this is the equation also that has been studied quite a bit. There's a bunch of references here, but of course, because you don't have 1 minus u, this is not an equation that preserves this natural bound u less than 1, right? It can overshoot. You can have solutions that take value bigger than 1. In fact, traveling wave, which exists, right, in some regimes, so I think what it depends a bit is on the coefficient that you put in front of the u here. I should put some mu coefficient. Depending on the mu, traveling wave can actually take value bigger than 1 and have some oscillation near the front. So it's not quite as nice properties as the usual KPP. All right, so now, so this is kind of the model we had in mind when we started this. So now let me show you a few videos that again were shared by Gabi in part of the experiments in her lab, and tell you why we were not satisfied with this model. So this is actually the same video that I showed you initially, and shows how the colony is expanding in space. But again, the population occur because there's no active motion, but because of this mechanical interaction, this pushing, right, that occur when they double in size to get mitosis. And congestion is fundamental, right? It only expands in space because it gets congested. You get to that maximum density, kind of u equal 1. And so when they grow, they have to push people around. Another thing that's interesting is because cell is only going to move if it's being pushed by someone. As soon as it moves, it's being replaced by something, right? So the density should always be monotone increasing in time. It never, there's no reason to go down. This is not something you have with reaction diffusion equation, right? The KPP equation or even the nonlinear one, solution can be decreasing because they can spread even without growth. And when they spread without growth, then they can decay, right? Now the traveling waves are monotone in time for those equations. Now, this is another video that she showed us, and it's okay, I started, but you will see that looks like nothing is happening. Now, if you focus here, if you look here, you'll see that there's a hole, there's no cell here, but if you wait, we wait long enough, eventually the hole will fill. So why is there nothing happening? Because it's completely saturated, right? So this video was taken in the center of some colony where it's already, so you see the hole that I was showing you here is gone, and since the movie is over. So what happened here is because of saturation, there is nothing much can happen. The cells are unable to double in size and experience mitosis. There were a few holes because of friction, and so those holes eventually got filled, right? But that's about it, right? So there is this notion that, so Gabi told us earlier and about that was very important for them is this notion of jamming, right? There's this idea that when you have a lot of cells, they get kind of stuck and they're unable to move. And if they can't move, they can push, and then they can't experience mitosis. Mitosis requires this doubling in size. That cannot happen. So, but importantly, of course, this is very much something that depends on where you are in the colony. The colony will be affected differently by this high density, depending on whether you are in the center of the colony or near the edge. And this is a movie that shows what happened near the edge. So here you have your cell and you have the front. And here what you see is the front moving. So that's a kind of a close-up on the edge of the colony that is expanding. And it's not easy to see, but if you were to look carefully at what happened to some of the cells that are at the front exactly, you notice that once in a while, some of them divide, but mostly they're just being pushed by the cells that are dividing behind, right? So there is this kind of, there is this region, right? There is a region near the front where there is a lot of mitosis, and as the cell duplicates and grows, they are pushing the fronts that are ahead, and that pushes the front forward, right? While, as I was saying earlier, there is an inner region which is much more congested and where not much is going on, right? And so this sectioning of the colony is something that they really insist on, the biologists, and that this Healy show type model I discussed don't really capture. All right, so now let me tell you a little bit about the model that we came up with after discussions with the biologists. So we still wanted to have a continuum model. So I didn't mention here in my very brief review of models that I knew about, I didn't discuss much the model I don't know about. And especially so for biologists, they use a lot of individual-based model, right? So models that tracks individual particles. For them, it's very easy to write simple microscopic model and put that into their computers to do simulations. So I didn't discuss that. We wanted to stay at this level of continuum models that describe the evolution of a density, so U, and still includes a pressure, P. We have very clearly for us this notion of congestion, it's maximum packing density. You cannot take value bigger than 1 that corresponds to the maximum packing of the density. And we'll normalize the pressure to be 1 where when U is 1. And so the first thing is clearly from the last video I showed you, right? It shows that even when U seems to be 1, there can be mitosis if the cells are able to make some space by pushing the nearby cells around, right? So we go back to a term for the local rate of mitosis that looks a bit like the non-local KPP term that I mentioned earlier, where you can have mitosis as long as in some neighborhoods there is some space and that allows the cell to push its neighbors to make room for the daughter cells. So G of U in this term will be the rate of growth when there's no competition for space. So typically you can think of G of U to be U. That's okay. And so this K convolution with 1 minus P is something that measures the level of congestion in some neighborhood of X, right? So the K is really what represents the ability of cells to push their neighbors. So it really encodes all of this mechanical movement, kind of mechanical interaction, sorry, of the cell with its neighbors. And for us, the way jamming that I discussed is taken into account is this assumption that K is compactly supported. So this can only take place over finite distances, right? So L is finite. It's of order of many cells length, right? So it's much bigger than the left-hand cell, but it's much smaller than the size of the colony, right? So yeah, at the end, L will be essentially the typical width of this active rim, right, at the edge of the colony. Okay, so K is compactly supported. You get very different behavior, very different behavior for the solution if K is not compactly supported. We'll normalize it to be integral 1. And now we look at what happened when mitosis takes place, right? So if U is less than 1, then the pressure should be small, and then when you have mitosis, daughter cells can stay wherever they were. There is no need to push anyone around. Everything can be local. But when U is close to 1, and then when you have crowding, then as a cell duplicates at the point X, it might have to push its neighbors, and the neighbors might push someone else, and so on. There may be a chain of pushing. And what happens at the end of this chain of pushing is that an empty space somewhere else will be filled. Right? And so there is a kind of cellular rearrangement that takes place, right? And so what we say here is that F of U is the rate of mitosis, but the actual increase of U, right? How much the density is increasing at X, right, is not quite F of U. It's F of U times 1 minus P. So when P is 0, it's F of U. When the density is 0, all the cells stay where they are. But when the density is close to 1, the cell have to go somewhere else. The cell actually is not actually going anywhere else. It's just pushing someone who's pushing someone who ends up filling a gap somewhere else. And so, this is the term that really is a contribution to the increase of the density at U due to local mitosis. Now I can rewrite this term like this. This is just, I mean, f of u times 1, and f of u times p, I rewrote it like this just to show you. So this is how much mitosis is taking place. And this is the loss term, right? This is terms that corresponds to things that should have stayed at x but moved to some place y. And so by symmetry, right, if this happens, it means that there will be mitosis at a location y that will lead to an increase of the density at x. And by symmetry, that's the term you should have, right? It's exactly the symmetric of this guy. I just switched the role of x and y and nothing else. And so what you end up with is this equation, right, where dtu is a sum of two terms. The first one is this mitosis rate, which again looks very much like the non-local KPP term, except there is a pressure instead of u, but otherwise it's a similar form. But L, on the other hand, is very different from our usual Laplacian. It's this cellular rearrangement. It looks much more like a Boltzmann-type operators that move things around with a loss term and a gain term. And so those two terms that I wrote, right, the first term is a gain term. It's the increase of density at u because of mitosis that took place at y, and then the other guy is reverse. This L is a conservative operator by symmetry. You can check the integral is 0, so it doesn't add any mass. It just redistributes the cells. It looks a bit like some of the non-local dispersion operators that I mentioned earlier, but it's different in several ways. I mean, first, it's very much nonlinear, of course. And very importantly, right, so this is the only thing that will generate any kind of motion. So that's the only operators that will indeed lead to some spatial expansion. But you see that the operator involves G and involves P, right? So without G, if G is 0, the L is 0. So without growth, without mitosis, there is no movement. Again, this is going back to the idea that cells are immotile, they don't move unless there is proliferation and congestion. In fact, if P is 0, right, if there is no congestion, then again, right, L is 0. Without congestion and without growth, without both of those things, there is no L, and so there is no motion. We can, so this is very much a non-local and nonlinear model. We can relate it to our local model, I mean, because that's where we came from again. I mean, we like our reaction diffusion equation. There is this parameter L, right? I mentioned that K was normalized, the kernel K was normalized, and that it was supported in a ball of size L. So let's take it to be like this. And then you can see what happens when L is very small. So when L is very small, this L of u becomes this operator here, this divergence form operator. So there are two terms, two flux, right, in this thing. The first flux is a flux away from the crowded region, right? It's proportional to the gradient of the pressure. So it's really moving, cells are moving away from crowded region, but it's proportional to the growth, right? So there's no reason for cells to move away from crowded region unless there is some kind of mitosis that is, again, leading to this pushing. The second term, right, is proportional to this growth rate, right? It's the gradient of the growth rate, but it's modulated again by the pressure now, and it's a very much a degenerate drift term because it vanishes both when P is 0 and when P is 1. So it degenerates both when it is when it's congested and when it's not congested. Okay. So this is our first kind of model. But like we did earlier with the initial limit, right? We wanted to see what happened if we take this. Sorry, before I do that, let me just show you that. So what's nice about this model, it has good properties in the following sense. I can rewrite it like this. Right? So just trust me, I did nothing here, just put the terms in some different order. What's important is I was able to factor the 1 minus P. And that means because P of 1 is 1, that if U is less than 1 initially, it stays less than 1 for all time. And P stays less than 1 for all time. So this idea, right, which I didn't quite enforce, I'm not putting that as an extra condition, right? But it comes out of this cellular, the way I built in the cellular rearrangement operator guarantees that U never exceeds this maximum packing density. And once you know this, the P is less than 1, then you can see that all the terms are non-negative. So we have also the fact that U is monotone increasing in time, as I said initially, was something important for us, this idea that the density should never decrease. Nevertheless, it's a nonlinear, non-local model, continuum model. Again, the simplest case you can think of is take G of U equal U, P of U equal U gamma. But what we like to do now is look at the limit, right, gamma goes to infinity. A bit like I did earlier with Illy-Shaw, right? The idea here is to say, okay, what happens in this extreme situation where we say this pushing only happens when U is 1. This is what it is, right? So when U is less than 1, the pressure will be 0, and all growth is purely local, right? As soon as I reach that saturation, as soon as U is 1, then I start having this kind of dispersion. So the model simplifies a bit, so because, well, so here nothing fancy, G of U times P becomes G of 1 times P, since U has to be 1 if P is not 0. And then you notice that because dtu will be 0 in the set where U is 1, this equation reduces to that, G of 1 times 1 minus P. So as long as G of 1 is not 0, so as long as there is some mitosis that can happen when U is 1, then this means that P turns out to be exactly the characteristic function of the set where U is 1. Right? So things simplifies a bit. This is not the case for the Illy-Shaw limit I discussed earlier, but in this case, P is simply this characteristic function. And so the model becomes this one, right? You have, so it's more singular, of course, but it writes a bit nicer. So the first term, the dtu, so when U is 1, dtu is 0. When U is less than 1, dtu is the sum of two terms. The first term is exactly our local mitosis rate, right? The one I wrote earlier, G of U, 1 minus K convolution with P, except now P is this characteristic function. The second term, right, is the addition of cells at X due to proliferation that took place in the saturated region, right? So if in the saturated region where U is 1, there is some mitosis that can lead to, there will be pushing because it's saturated there, and that will add a cell at the position X. I can think of this as an obstacle problem for those who like obstacle problems, because, so it's in time, of course, because I can write it in this form. I can say U is less than 1, dtu is less than this right-hand side with equality when U is strictly less than 1, or I can write it in this form. Okay, this is just for this for those of you who like obstacle problems. But it is a free boundary problem, and it really provides a geometric description of the evolution of this set, right? The set where U is 1, this saturated set. I can also think of it, right, because there is no Laplacian in there. There is no. I can think of it as an infinite system of coupled ODEs, right? I can for each x, I can solve the equation here, dtu equals something. They're coupled because of the convolution, right? The K convolution. But this is a good way to define notion of solution, but it's a terrible way to study the behavior of solutions. The general shape, right? I mean, what we get here is a model that has this general form, right? I rewrote it here a bit differently, but it's the idea that it's something that captures spreading of a colony or any kind of population because of a combination of the local growth, the term G of U in blue here, and this dispersal that comes out of the saturated region, right? So this H of U times K convolution U equal 1, right? Which is an influx that comes from nearby saturated region. And we've talked a bit with other people, and it seems that this is a fairly general mechanism that can be applied to other frameworks in particular. So Henri has some colleagues that works a lot on urban sprawling, so how cities evolve and grow. And this is the type of model that is interesting for that framework, where you have, so the saturated region in that case would be the urban core, where you can't add anything because there's no more land available. And when that happens, then people start building a little bit outside at proximity of the urban core where all the services are available and everything, but a little bit nearby. And that leads to this kind of non-local dispersion term, right? That you add things in a neighborhood of the saturated region. I should mention also that it looks a bit like, I mean, we found in the literature some models that had some kind of similar flavor, at least, not exactly the same, but similar flavor for the spread of animals. Skellam, I think the Cott and Lewison was for butterfly, but you have model of this form that have a bit of a similar flavor of a local term and a non-local dispersal term. Those models do, and the neural field equation that has been studied quite a bit in particular. I mean, some paper on that equation, but none of those models, at least none of the one we found, really first took into account congestion and led to solutions that would be monotone in time like we wanted. But there are clearly, right, some similar flavor here. All right, so let me talk a little bit about the math that we can do. So as I mentioned, this is very much a singular non-local equation, obstacle problem type. On the other hand, what we have that's very nice is solutions that are naturally monotone increasing in time, and in fact Lipschitz in time, because DTU here is clearly going to be bounded, right? On the other hand, there's no Laplacian, so there's no regularizing mechanism in X. But we can show that if solutions start Lipschitz, for example, they stay Lipschitz, right? Or if they start C alpha, they stay C alpha for all time. All right, so I'm not going to go through a very precise statement, but typically, so we assume that K is at least BV. We say BV because we want to be able to take K to be the characteristic function of the ball of size L, let's say, right? But it doesn't have to be, but the G, the gross term is Lipschitz, non-negative, G of 0 is 0. Very importantly here, I wrote that, so typically you would expect G to be monotone increasing. It doesn't have to be, but some of the property I mentioned requires this idea that G of U is less than or equal to G of 1, right? Which you could come up with situation, especially if we start adding the role of nutrient, where this is no longer the case, and that makes things harder. Okay, so here it's very brief summary of what we can prove. We can prove existence. Now, the way we prove existence is actually by going back to the first nonlinear model I wrote, one with the P of U equal U to the power gamma, because that model is much easier. You can use Cauchy-Lipschitz, you have existence immediately, uniqueness as well. And so then what we really do is actually justify the limit gamma goes to infinity, right? So I mentioned we arrived at this singular model, right? Remember, by taking this very particular pressure law, P that is 0 or infinity. So here we actually justify that this is what you get in the limit gamma goes to infinity for the non-local nonlinear equations that I wrote initially. Uniqueness, which was obvious for the nonlinear equation gamma with the gamma finite, is no longer obvious at all. It turns out though that it follows from a comparison principle. So you have a comparison principle, which interestingly, we are not convinced that the original equation has a comparison principle, but this one does. So, and the reason it is really because we are really to prove the maximum principle. It's not trivial, right? Because it's non-local. It's because of the non-local term, and it's very singular, right? So if instead of characteristic function of U equal 1, you had a nice smooth function of U, you could get away with things for uniqueness. You could prove uniqueness easily. But because of the singularity, it's not so easy. But you have the maximum, you have a comparison principle, and that is obtained really by tracking the behavior of the free boundary. So looking at when free boundary cross, and you can prove uniqueness, comparison principle. Invasion, so that's intuitively, I mean, where I said U is monotone increasing, so it makes sense that if you start with something, eventually they will colonize everything, right? So U converges to 1 as t goes to infinity. And then we have this property, right, which was important for us because this is one of the things that the biologists really were looking for. If the support of the kernel K is exactly the ball of size L, right, then the support of the solution U at time t is exactly the congested region where U is 1 plus the ball of size L. And that's for t large enough. Large enough is just so that you want to make sure that the support overtakes the support of the initial condition. Sorry, the saturated region. You want the saturated region to overtake the support of the solution at time t equals 0. And so what this tells you, right, is that there is really, right, I mean, there's 3 regions really. There is a saturated region where U is 1. There is a ring of size exactly L around that saturated region where U is between 0 and 1. And then there is a region where U is 0, right? So we have now this nice kind of sectioning of the colony that we wanted. And then finally, right, because again, coming from the KPP community, we wanted to know if we also could have traveling wave, if we could describe more precisely now how that spreading occur. And so what we can show is that there are indeed traveling waves, right, for this model. So planar traveling waves with a direction E, speed C, and it's exactly the standard result that says that there is a minimal speed C star. There is a traveling wave for all C greater than C star. It's unique up to translation. So let's say if I fix the saturated region to be exactly minus infinity 0, then there is only 1. There are no traveling waves for C less than C star. And a bit as in the degenerate KPP type equation case, we can show that for C bigger than C star, the traveling wave is strictly positive everywhere. So this does not correspond to any kind of physical situation we're interested in, right? But the traveling wave with the minimal speed is compactly supported, semi-compactly supported, right? So it's it's saturated region is a negative real line, and the positive, the support is from minus infinity to L, right? So you have this little ring, right, from 0 to L, where phi takes value between 0 and 1, and then it's 0. And so intuitively, we expect that this compactly supported traveling wave with a minimal speed is the one that describes the spreading of an initially compactly supported initial data. And indeed, right, we can show, so this kind of weak, this is the first kind of weak result, but it shows that if I take an initial condition that is Lipschitz compactly supported, and I look at the solution at time t, and I move in any direction E, with a speed c that is bigger than c star, then eventually I'll arrive 0, okay? And the idea is that if I move in any direction at speed bigger than c, eventually I will overtake the colony and I will end up in a place where there's no one, right? But if I do the same with a speed less than c star, eventually I will find 1. So if I travel again in any direction, but at speed less than c star, eventually the colony will overtake me and I will be in the saturated region. So this suggests that the colony is moving with that speed, is spreading, sorry, with that speed c star in every direction. We don't have a formula for c star, I mean, not an explicit formula, we have some estimates, and we know that it's of order L. Right? So this parameter L, right, that comes from the kernel K, right, is also determines that speed of propagation. All right, so let me end with some numeric. So a thing that is very nice about this model is there's no Laplacian. All there is a couple of convolutions. It's extremely easy, even for someone like me, to simulate it numerically. I'm not particularly talented, but this is really simple. And so this just shows, for example, here, initial colonies that is going to go. So the black region is the saturated region where the U is 1, and the blue curve shows the edge of the support. It was not easy to show, but outside of the blue curve, U is really 0. And so you can see how there's this kind of ring, right, between the black region and the blue curve where U takes value between 0 and 1, and it is spreading. Now, because it's so easy to write the equation and to numerics, it's also very easy to change a little bit what you're doing. So for example, what we did next was we wrote the same model, but with 2 species, right? So we have now we have 2 types of cells, the green and the blue, and they're competing for the same space. So the limitation is that the total density, the sum of the 2 has to remain less than 1. But otherwise, sorry, the idea is the same. So in this first movie, right, the 2 types of cell are growing at the same rate, and in the second movie, that is the green one goes twice as fast. So the green one is going to sort of go engulf the blue guy. Okay. So this is, I mean, the biologists love to do experiments like this with different cells. They can put markers in the cells that it's very easy for them to see that to make movies where you can really see. And so in particular, that type of front here, where there's a little bit of mixing of the 2 types of cell, I mean, it's something that they observe and they really like to see. So that was the motivation for those movies. And then the very last thing I wanted to share was this, because this was actually also one of the early problems that Gabi Steinbach mentioned to us and that we wanted to try and capture. So here what you have on the left is some experimental picture. They have 2 strain of some bacteria that can compete. One of them, I don't remember which one, let's just say the blue guy, but that's random, can kill the other one. So when they touch, right, the blue cells will kill the gray one. And if you think of just an experiment where you put in a box two types of cells that can both proliferate, but one can kill the other one and the other one cannot kill the other guy, you'd expect at the end there is only one guy left, the one that can kill the other one. Right? And it's not the case. Right? What they have is this picture. The red things are dead cells. So what happened is when they touch, some cells die, but the dead cells stay there, and they form this kind of ring, right, that protects, that separates the two strains. And so at the end of the experiment, you have about the same amount of each of the cells. Now, so here what we did is, again, with our same model, we have now three species. We have the same ones, the blue and the green. So the blue can kill the green one in this setup. And you will see some red cell appear, and the red cell are the dead cell, right? And so when the cells are dead, they belong to a new species. They don't proliferate, obviously, but they're still there, and they contribute to the congestion. And so what you see is something similar occurring, right? Where, well, when they meet, cell dies, but then because of congestion, they can't mix anymore, and you have that same type of kind of ring around the green guy of dead cells. And this is something that was hard to capture with other models, right? If you think reaction diffusion equation, KPP, for example, you will not see this, right? With KPP, the blue will win because diffusion allows cells to go inside and start killing the guy from inside, and then there'll be nothing left, right? So with any kind of KPP, even non-linear KPP, this will not happen. Right? And with Illy-Shaw, there's nothing happen. I mean, with Illy-Shaw, adding killing doesn't change anything because when the two colonies get in contact with each other, the row is one on both sides and nothing can happen. So there's no opportunity for even killing. Okay. So this is one of the things that was one of the phenomena that we were hoping to see. And so numerically, at least, it looks like satisfying. All right, so that was the last thing I wanted to show you. So just a brief summary. So this is a model, right, that we tried to develop to really capture this spreading of immotile cell colony. What's important was to capture this notion of maximal packing density. We wanted monotonicity in time, and those two notions of jamming, right, the frozen core kind of thing, and the partitioning of the colony, right, with the active rim outside. It actually turns out that the model has good mathematical property, and it's very easy to simulate numerically. There is a lot of things we still want to do. So in particular, right, I mentioned with traveling wave, we have existence, and we show that the minimal speed of the traveling wave probably captures the spreading speed. But of course, people who are familiar with reaction diffusion equation know that there's a lot more you can try to do. Stability of the front, very precise tracking of the position of the front. So mathematicians love these kind of things. Of course, you can incorporate a lot of other phenomena into the model. It's actually quite easy. One thing that I'm particularly interested in is this last step here. I mentioned, like at some point, you know, when we take the L goes to 0, this small parameter L, our equation can be approximated by the reaction diffusion equation. Is a very degenerate type of diffusion, right? Doubly degenerate at 1 and at 0. Another thing that I didn't put here, which would be something, but mostly we want to talk about some more with the biologist, is here we're assuming everything is happening in 2D. It's not quite true. Because as it gets really congested, the bacteria are very happy to just go upwards. Now, why is it still mostly 2D? It's because the nutrients are on the surface. So even if they can push upward a little bit, the bacteria that end up don't have access to the nutrient and they don't proliferate. But still, right, they do a lot of experiments. So there's plenty of paper in biology that focus on just the 2D aspect, the view from above of the colony. But there are also a lot of work done on trying to capture the shape, the height, right, of the colony, and what is exactly that shape and how it happens. So this is something we completely ignore in here, right, this additional dimension, but it would be very interesting to also take that into account. And that's it. Thank you very much.